this video, we're going to talk about Syn additions to alkenes. And what that means is we're going to take a reaction that turns a double bond, a carbon-carbon double bond, into a carbon-carbon single bond by adding two groups, one to each end of that double bond, with the same stereochemistry. Now, one reaction that you've seen from the very start of the course that did this kind of a reaction was H2PDC. We've been using it for synthesis, and if the professor chose to stress it, you've probably been using it for other things too. The point being, though, is that when this reaction occurs, what H2PDC does is it turns a carbon-carbon double bond into a carbon-carbon single bond by adding a hydrogen to each end to each carbon that was involved in that double bond. And the Syn addition aspect of that means that those two hydrogens come in with the same stereochemistry, meaning either they both came in on a wedge or they both came in on a dash. Now the important thing to notice is this methyl was on that double bond when this reaction occurred. When you are attached to a carbon-carbon double bond, your geometry is trigonal planar. You are sp2 hybridized and you are flat. The second you get rid of that double bond, you become tetrahedral, and that means you're going to have stereochemistry, wedges and dashes. And what you can just do is, whatever stereochemistry the hydrogen comes in on, the methyl must be pushed to the opposite side. Which means in this example, since the hydrogens come in on the wedge, the methyl gets pushed to a dash. And in this example, the methyl gets pushed to a wedge. And so in the case of H2PDC, that's all there is to it. You don't have to worry about any mechanisms. This is one mechanism you'll never be responsible for. Just know that each end gets a hydrogen added, and those hydrogens will come in with the same stereochemistry, effectively giving you two enantiomers, assuming the molecules are chiral and they can be enantiomers of each other. Now let's look at other Syn additions. Now, the nice thing about the Syn additions is actually none of the reactions you need to know that are Syn additions, you don't need to know any of their mechanisms. It's just know the reactant and know the product. Well, the starting reactant is always the same. It's something involving a carbon-carbon double bond. Now let's talk about what could we get. One Syn addition that you can do is osmium tetroxide, OSO4, and pyridine, step 1. Step 2, what is it? NaHSO3 with, I believe, H2O, yeah, H2O. Okay, so that's a whole lot of stuff on one arrow. But we don't care about that. We don't care about that. The second you see OSO4 over the arrow, this is literally the only time we ever use this reaction, save for one other situation. And for the record, OSO4, osmium tetroxide, the same exact reaction I'm about to describe can be done with KMNO4. Again, notice the O4. These are oxidizing reagents. And what they do is they add oxygens. Now, specifically about KMNO4, it needs to be cold KMNO4. When we talk about oxidative cleavage, you'll see why there's this specification about temperature. But for your purposes, if you see cold KMNO4 over the arrow, or osmium tetroxide over the arrow, regardless of whatever other fluff is on that arrow, we know what reaction we're doing. We are doing a reaction that adds, instead of hydrogens like H2PDC, adds OHs, Syn to each other across those two carbons of the double bond. Meaning, we could have the situation where those two OHs come in on a wedge, and that means this methyl would be pushed onto a dash. Or we have the situation where both those OHs are added on a dash, and that means this methyl will be pushed to a wedge. And again, no mechanism needed. If you see this over the arrow, you know all you have to do is add two OHs Syn to each other. The next reaction that can go over our arrow from our Syn addition list is a reaction called hydroboration. And now this reaction depends on when you take the course on how much detail you need to know about it. So first of all, what does this reaction look like? Over the arrow, you will see step 1, BH3THF. Step 2, H2O2 in water. Okay, so again, a whole lot of stuff This one, unfortunately, we can't really eliminate anything, but really it's the only time you ever see BH3. So if you see BH3, we are doing a reaction called hydroboration. And what this reaction does is it adds a hydrogen to one carbon and an OH to the other. And the rule is the hydrogen gets put on the higher degree carbon of the double bond, and the OH gets the lower degree. So what does that mean? Let's look at this structure and see. Well, I have a tertiary carbon on the left and a secondary carbon on the right. Based on this rule, the hydrogen goes on the higher degree. That means the hydrogen would go on the tertiary carbon. I'm going to say, let's say it comes in on a wedge. That means the methyl will be coming in on a dash. So here is my hydrogen. The OH goes on the lower degree of the double bond, meaning the secondary carbon. And again, since this is a Syn addition, that OH must have the same stereochemistry as the hydrogen we added. So the OH would look like that. And of course, we have the other possibility where the hydrogen and OH come in on dashes. And that means the methyl will be wedged. Okay? So that is the idea of hydroboration. Now I said depending on when you take the course, there's a little more detail you need to know about that. What I'm about to talk is a little more specific to the summer course. The summer course, there's two details that are stressed. And now, this is sometimes stressed in the main semester, but it really depends on the professor's time, if he wants to talk about it or not. And what that point I want to make is, where does the hydrogen come from, and where does the OH come from in our reactants over here? Well, straightforward enough. The hydrogen is produced by the BH3, and the OH is produced by the H2O2. Now, why does that matter? Because, especially in the summer course, a question that I see very often is, what if instead of BH3, they gave you BD3, B-deuterium-3. Deuterium is just like hydrogen. It does everything the same. It's just an isotope that we can use to keep track of where our hydrogens go. And we could also do, instead of H2O2, we could do D2O2. And the point of these questions is to track, okay, so which of these adds where? And let's say we also put a D2O here. Now, I'll do that last. Actually, let's not do that. Let's just keep this H2O for now. So, what this shows is BD3. The hydrogen is added by the boron part, which means that red deuterium would be over here, or over here. D2O2 is the green hydrogen, or the green deuterium, which means the D that's green would be on the OH. Okay? Now, what if neither of these were deuteriums? What if they were just hydrogens, but we made that water deuterium? So BH3, H2O2, so this part's the same, but now we say D2O there. Well, if that were the case, there would be no difference from what we drew initially. The H2O in this reaction has nothing to do with adding anything to that double bond. It has other parts to do with the mechanism, but since you're not responsible for that mechanism, why care? So, if it's just the H2O that is deuterated, there won't be any deuterium in your products. So once again, just to stress it, if the H2O2 has a deuterium in it, your OH that you add will have a deuterium in it. If your BH3 has a deuterium in it, the hydrogen you add will have a deuterium in it. And as long as you know those rules, there aren't really many tricks we can throw at you involving this question. Just remember that the OH gets added to the lower degree, the hydrogen to the higher degree. There is one last Syn addition that you may or may not be responsible for. It depends on the year, depends on the professor, and it depends on if they feel like stressing it or not. This last reaction is what's called a Carbine reaction. And again, it's a reaction whose mechanism you don't need to know. The way the Carbine works is over the arrow you will see CH2, I2. So a carbon with two halogens on it. And under the arrow, and I believe in the past I have seen CH2, NH2? I'm not sure. For now, let's just leave it at this. CH2, NH2, and then under the arrow there's zinc with some copper. At least as far as I've seen in the textbook. And again, this is a reaction that you very often is skipped in the semester. I'm just mentioning it in case. And what this reaction does is it actually makes a three-membered ring across your double bond. So what does that mean? This carbon right here, if I were to label it in green, would be added, say right there. And the two carbons that had the double bond will be connected to that green carbon by either two wedges, because again this is a Syn addition, or two dashes. So what this makes is a three-membered ring, where your double bond used to be. Another mechanism you don't need to worry about, and that's really all the Syn additions you have to know.